Hey everyone, welcome into this lecture video on trig integrals. So these are integrals involving trig functions. In this video I'm just going to do a bunch of examples. So in the lecture notes I told you you need to know your trig identities and you need to know how to use them. In a course where most of your assignments are online, knowing the trig identities just means that you know where to find them, right? But there are certain trig identities that you should memorize and should know by heart. And as we go through this list of examples, I'm going to do 6 examples here. As we go through these examples, you'll see that some of them are kind of frequent. They show up frequently. Okay, they're frequently used. So let's start with this first integral, and this is one that you will definitely need to know an identity for. So this is the integral of sine squared dx. I'm going to kind of build on this integral. Well, not really build on the integral, but build on the integrand as we go through this lecture. So as of now, we only know a couple different ways to integrate functions, right? So we know what I call the stair at it method. You just look at the integrand and ask yourself, do I know a function whose derivative is sine squared of x? And probably the answer is no, right? Just by staring at it, just by memory, we probably don't know an answer. So the other options that we have are we can do a u sub, but remember that if you make a u substitution, then you have to have the du. So if you tried to make, so the only real option here would be if you tried to make u equal to sine of x, then you would need your dx, right? You don't get to choose this, right? You would need to have du equal to cosine of x dx, and we don't have it for this one, right? We don't have that. So this is not going to work either. So u sub doesn't work. And then we had integration by parts, and we could try to break this up and apply some integration by parts to it, but it's probably not going to work. So a better option for this one especially is to apply a trig identity to the integrand. So I'm sure we remember that sine squared x, if we have sine squared, then I think it's called power reducing. It might be called the double angle formula, because what happens is with sine squared, what you end up getting is that this is equal to 1/2 of 1 minus cosine of 2x. All right, and then the kind of the other power reducing or double angle formula is for cosine, and cosine squared of x is equal to 1/2 of 1 plus cosine of 2x. All right, and so these are two that you definitely should know. So commit these ones to your memory and make sure you know how to use them more importantly. So what we're going to do is we're going to take this one, right? We're going to take this identity and plug it into this function. And so what we'll end up with is the integral of sine squared x dx is equivalent to the integral of 1/2 times 1 minus cosine of 2x dx. And then it turns out that we can integrate this one, because this one, the integrals are always linear, right? So this 1/2 can come out. And then we can just do this in pieces, right? You can do individual antiderivatives when there's a plus or a minus sign in between in single pieces. The first one's just going to give us x, right? So we've got our 1/2 of x times x. And then we have a minus here. Here's what I'm going to do. I'm going to redo this one because we need to do, maybe we could do this in our head, but let's do a little bit of u sub here just to make sure we understand why this one is what it is. So at this point, we need to make a u substitution for the 2x, right? We want this to just be cosine of u. So we'll let our u equal 2x. And again, we don't get to choose our dx, right? We don't get to make that choice. So what are we going to do? We take the derivative. Du is then 2 dx. And we ask, do we have it? Well, no, but we're close, right? We need a 2. So we can squeeze a 2 in there, but that means we have to divide out another 2 out front. All right? And so what we end up with then, we've got our 1/2 x minus, this integral now becomes 1/4 integral of cosine of u du. And that one's easy to integrate, right? So the integral of cosine is sine, positive sign, and there's a minus sign here. So this all becomes 1/2 x minus 1/4 sine of u. But what's u? We have to put this back in, right? So we'll put back in sine of 2x plus c. So this is the integral of sine squared x dx. All right, so there's our first example. We're going to do a bunch more now. So our second example, I want to build on this a little bit. And again, I'm going to put a similar looking integrand, but it's not going to be the same. So this time I'm going to have it be sine squared x times cosine squared x dx. And so now we have two of these, right? We have a sine squared and a cosine squared. And so what you might think, and I hope that your first thought was, hey, we could just use each of these formulas, right? And we could multiply them together. And you absolutely can, but I want to remind us of another trig identity, just so that we see it in action. So yeah, so just so we're clear, one way that you could solve this integral is to just plug in both of these power reducing or double angle formulas and then multiply them together, and then you'll have to use another power reducing, you'll see, but that's okay. All right, so on this one, here's another identity that we can try to use. So sine of 2 theta, I'm going to use theta here, is equal to 2 times sine of theta times cosine of theta. All right, and why is this helpful? Well, we've got sine times cosine, so if we squared this whole thing, look what we get. On this side we have 4 times exactly our integrand, right? Sine squared theta, cosine squared theta. So actually what's in our integrand here, this term, can be replaced by 1/4. You have to move this 4 over, right? 1/4 times sine squared of 2 theta. All right, so why is this better? Well, maybe it's not better, but the reason that I like this one better is because we just did the integral for sine squared, right? So now what we need to do is go back and plug in, this is not 2 theta, this is a 2x, right? Because this is for our exact problem here. But we just did the problem with sine squared of x. So what we need to do is get the 2x in there, okay? And so that's easy to do. We just do a u sub, right? So this integral is equal to 1/4, just by this trig identity, right? Just by using trig identities, we reduce this to a problem that we literally just solved. So it becomes 1/4 sine squared of 2x dx, that's the integral, right? And then we're going to make our u sub. So our u is 2x, our du is 2 dx, just like before. We don't have the 2, so we put it there. That means we need to divide it out here. And now we end up with 1/8 integral sine squared u du, but look at, we know exactly what the integral of sine squared u is because we just computed it, right? What we have to remember is to put this 1/8 here and then make the substitution here. So I'll do it in 2 steps. So we'll keep the 1/8. Based on our previous work, this is the answer, right? So this is 1/2 x minus 1/4 sine of 2, whoops, these are u's. I'm just copying. I shouldn't have copied, right? This is a u, so this has to be a 1/2 u minus 1/4 sine of 2u, and then our plus c goes out here. But at this point, we need to get our 2x back in for our u, right? And so the final answer here is that we get 1/16 times, well, here, I'll do it in 2 steps because we got a 2, there's a 2x going in for u, right? So 1/8 times 1/2 times 2x minus 1/4, that one's not going to change, times sine of, that'll become a 4x, 2 times 2, plus c, and then this all gets distributed, and so here's our answer. The integral of sine squared x times cosine squared x dx is equal to 1/8 x minus 1/32 sine of 4x plus c. All right, so like I said at the beginning of this problem, we could have done this one by just plugging in each of these 2 formulas for sine squared and cosine squared, doing a little arithmetic, and then carefully applying it again because you get a cosine squared out of it, and you would get the same answer. But on this one, the way I did it, the reason I did it this way was so that we could use our previous answer for the integral of sine squared. We get this answer here, right? So after just carefully doing a trig sub, we end up with the integral of sine squared times cosine squared dx is 1/8 x minus 1/32 sine of 4x plus c. All right. Next example. I'm going to stick with the sine squared x, but this time I want to put cosine cubed x dx. So notice up here, this is a cosine squared, right? And this is a cosine cubed. And what you might be thinking is, well, if we continue this train of thought where we use the previous one to solve the next one, then we would have to write this as the integral of sine squared x, cosine squared x, cosine x dx. And at this point, we have a product, right? So at this point, if we were going to try, which we're not going to, by the way, but if we were going to try to use the previous one, all of this would have to become our dv. This would have to be our u, okay? And Yeah. And so that would end up having to be integration by parts, and it would kind of be a mess, okay? It's actually way more work than we need, because what we can do instead is we can notice that if we make this be our u, I like the idea of making cosine be our u, then we have a u squared right here, right? So this term would become a u squared. And this term is not related right now to cosine, but it can be, all right? And it's related by the Pythagorean identity for trig functions. So we all remember that sine squared x plus cosine squared x is equal to 1 for all x, right? And so that means then that sine squared x, we can solve for this, right, is equal to 1 minus cosine squared x. And so if we make our u equal cosine, then we can get our sine squared in terms of u squared in this case, right? But in terms of u, because we can plug in a u for that cosine. All right, so I'm going to write this in a couple steps, and it turns out this one's going to be pretty straightforward. So we first swap out the sine squared with a 1 minus cosine squared. We leave this cosine squared, and then we leave this cosine x dx over here. I've done this all backwards, though, because I'm looking at this. I want this to be the differential. All right, so actually, my train of thought is okay, but I've made the wrong substitution because I want to choose my u so that the derivative is cosine x dx. So that means I need to actually choose my u to be sine, right? So I have to choose my u to be sine. So we're going to go back through and change this again. So this is not a big mistake. But in general, let's write down what our substitutions are going to be. If u is equal to sine of x, then du is indeed equal to cosine of x dx, okay? So that becomes the du. So that's the reason, that's what we're looking for, right? When we make a u sub, that means our u has to be sine, though. All right, so instead of solving this for sine like I did here, I have to actually, so this line wasn't going to be helpful with this substitution. Instead, what we need to say is, well, actually, cosine squared is equal to 1 minus sine squared x, and then we just have to swap these two. All right, so this then becomes integral of, leave this one as sine squared x, the first one, and change the second one to 1 minus sine squared x, and then our cosine x dx, that's all our du, and so now we're good to go, right? So this now becomes the integral of u squared times 1 minus u squared du, because now everything checks out. All right, and then we just multiply this out. This is a polynomial. So this is the integral of u squared minus u to the 4th du. That's, of course, 1/3 u cubed minus 1/5 u to the 5th plus c. And then we plug in, for u, we plug back in our sine. So we get that the integral of sine squared x cosine cubed x dx is equal to 1/3 sine cubed of x minus 1/5 sine to the 5th power of x plus c. All right, there we go. All right, I have a couple more. So this next one's going to be a little bit different. This one is not going to involve a sine squared anymore. So this one will be the integral of secant x dx. Now, this one is in the text. It's in your text, and what they do is a clever multiplication. So clever, they multiply by 1, which you're always allowed to do, right? But they use their 1 in this very kind of fancy way. They make, 1 can be something divided by itself, right? And so you can come up with different substitutions or different tricks that can become very confusing. So in this one, I'm going to do something slightly different. I'm going to do a different method that takes advantage of our knowledge of hyperbolic trig. So that's going to be very exciting, right? So we're going to solve a trig integral by invoking hyperbolic trig. Well, let's see what I mean. So in this one, we've got a differential here that looks like secant x dx, right? And we want to try to think of a function whose derivative is involves a secant x, right? So I think there's multiple ways to do this, but one way for sure is we can just let u equal tangent of x, and then if this is true, then what's the derivative? Well, the derivative of tangent is secant squared x dx. Now this is not exactly what we want right here, right? It's not exactly what we want. So what we can do then is divide through by one of these secants, and we can write this as 1 over secant of x du equals secant of x dx, all right? And so what I've done now is just move the secant from the top to the bottom, but I've got this du in here. I've changed the variable, right? I've got u in there. We need to get secant in terms of u. So is that even possible? And the answer is yes, because we have a Pythagorean identity just like the one we used up here. There's a Pythagorean identity that relates tangent and secant. Just take this equation and divide through by cosine, and you'll get tangent plus 1 equals secant, right? Squared. Tangent squared plus 1 equals secant squared. So this is an identity that relates tangent plus 1 to secant squared. Tangent squared plus 1 equals secant squared. And so at this point, what do we say? Well, all right, that's great, right? We can now take the square root to get this to be secant. All right, so this implies then that secant of x is equal to the square root of 1 plus tangent squared x. But of course, tangent is our u, so this becomes 1 plus u squared. Okay, so by the way, we're just assuming that we're in, say in between negative pi over 2 and pi over 2 for the theta here, and we'll talk about this later in the semester, why it's okay to make these kind of substitutions, and sometimes it's not. Sometimes you have to be very careful, but in this case, it's going to be okay. And so what we end up with then is that this integral can be transformed to, so this becomes 1 over secant, so 1 over this, right? This integral is transformed to 1 over the square root of 1 plus u squared du. And hopefully you guys remember, so we just studied hyperbolic trig just last week, right? So not too long ago. This is the antiderivative of arc cinch. Okay, so this is, in other words, this is equal to cinch inverse. Remember, that's what arc cinch means. Cinch inverse of u plus c. All right, just by looking at it, that's one that we should just know. 1 over square root of 1 plus u squared. All right, what do we do if, if that's not, hopefully you look it up, all right, if you don't remember that. But you need to remember your arc hyperbolic, your hyperbolic trig, your arc hyperbolic trig, all those different integrals that we got from those. All right, but what we really need to do, though, is we need to get the x's back in. So this is our answer in terms of u, but we weren't asked about u, we were asked about x, right? So we need to get this back in here. And remember, there's another formula for the hyperbolic inverse sign. Erase this equal sign. So the formula for hyperbolic inverse sign is that this is equal to the log of u, the argument, plus the square root of 1 plus u squared plus c. Well, the plus c comes from the integral, right? So this is a substitution that we can make. We can plug this into here, right? And so what we end up with now is their integral of secant of x dx is equal to this natural log of, I'll write it in 2 steps, so u plus the square root of 1 plus u squared plus c. And we just need to plug in. Well, what's u? U is tangent. What's the square root of 1 plus u squared? Oh, that's secant, right? That's secant. And so at the end of the day, what we end up with is that the integral of secant x dx is equal to the natural log of, I'm going to switch the order here, secant x plus tangent of x plus c. All right, so this is one, like I said, that's done in the book just by making a clever substitution or a clever change of the integrand. And what they do is they multiply both top and bottom by this secant x plus tangent x term. So in the book, here's what they do. And you're going to probably tell me that this is way easier. And as far as the computation goes, it certainly is. But the question is, how do you remember that this is what you should do, right? So what I've done in my method here is work it out in terms of a derivative, a differential that you can remember. So they multiply this all out, and then you can notice that this becomes 1 over u, or du over u. All right, this is a du over u. So you guys should work this out this way, as the book does. But however you get there, you need to know this formula. So the antiderivative of secant x is a natural log of secant x plus tangent x. All right. On this note, let's build on this one a little bit. So the next one, this is number 6. Let's do a couple more. So integral secant squared x dx. So we went from secant to now secant squared. Well, this one is really nice because we know this one is a stair at it, right? Remember I talked about at the very beginning, one of the methods for computing integrals is we just know the answer, right? And so this is the derivative of tangent. So this one's just tangent x plus c. Doesn't take any more work. So we like it when secant is squared, right? Secant by itself, hopefully we remember it, but if you don't remember it, it takes a little bit of work to get to it. Secant squared is very straightforward, right? It's just tangent x. And so then I'm sure you're wondering what happens if we move to, am I numbering these right? No, this should have been number 5. All right, so what happens if we then go to secant cubed, right? So this will be number 6. Secant cubed x dx. Well, secant cubed is just secant times secant squared, right? And we just did each of those, so let's see what happens here. Integral of secant x times secant squared x dx. We want to do a probably integration by parts here, right? So this, we have to, because this is a product. So we'll call this our u, and call this our du, or dv, sorry, our dv, because this one is kind of more straightforward, right, in some ways. So what happens then? Remember the integration by parts formula, we need our u, we need our du. So if u is secant x, du is secant x tangent x dx. If our dv is secant squared x dx, then our v is tangent x, as we just saw, right? We just computed that. And so then we apply our integration by parts. We multiply these, we integrate these, add, subtract, right? And this becomes what? Secant x times tangent x minus the integral of secant x times tangent squared. Tangent squared x dx. But at this point, we can, and remember this is all equal to secant cubed x dx. At this point, we can make a substitution, all right? So we can go up and we can remind ourselves, where did we have it? So right here, right? Tangent squared x plus 1 is equal to secant squared, right? So we can replace this tangent squared with secant squared minus 1, actually. All right, so I'll write this here. And this is just by using our Pythagorean identity. So once again, tangent squared x is equal to secant squared x minus 1. So when that goes in there, look what happens. We end up with, this becomes secant x tangent x minus the integral of secant x times secant squared x. So secant squared x minus 1 dx. And let's multiply this out and use the linearity of the integral. So this will give us a secant x tangent x. This is then going to be minus what? The integral of secant cubed x dx plus integral of secant x dx, right? And look at, this is the key. So this one looks like a copy of this one. We can move it over, right? We did this trick in integration by parts with one of our examples in the integration by parts formula. So this whole thing now says that 2 of our integrals that we're looking for, secant cubed x dx, right? 2 of these integrals is equal to what? Secant x tangent x plus this integral of secant. But we just did the integral of secant, so we can just write that one down. All right, hopefully you remember this, but at this point we just did it, right? So the integral of secant is this one, right? The natural log of secant x plus tangent x. So that's going to go there. And so now we've got that twice our integral, twice the integral that we want is equal to secant x tangent x plus the natural log of secant x plus tangent x, and then plus c, but we need to deal with this 2, right? So if we were only asked to find one of these, so what do we have to do? Divide through by 2, right? And so the integral secant cubed x dx is equal to 1/2 of this sum, secant x times tangent x, plus the natural log of secant x plus tangent x, and then all plus c. All right, and so there's how you integrate secant cubed x. You do integration by parts once, and then you use a careful Pythagorean identity. Now, the other way to do it is to use a Pythagorean identity first, and then very carefully, you have to choose a slightly different integration by parts, but you can integrate by parts, and then you'll get the answer the same way. It'll be the same answer. All right, so I got one more. this video is getting long, but that's okay because this is the only video for today. So here's the last integral. This one is the integral of 1 over cosine of x minus 1 dx. We want to try to integrate this thing. So looking at this, if you make a u sub, yeah, it's not clear. You wouldn't have the du, right? So if you try to make a u sub to get the cosine on top, you wouldn't have the du. So on this one, this is one where we can do kind of a trick similar to the book. But this one, it's a little more clear what we should multiply by because the bottom is a difference. And we think to ourselves, a lot of times when you see something like this, you think to multiply the conjugate, right? So multiply cosine x plus 1 over cosine of x plus 1. And that obviously doesn't change the integral. So what we end up with then is that this will be the integral of cosine of x plus 1 over the bottom becomes cosine squared x minus 1 when you multiply through, distribute. And remember that cosine squared minus 1, so it's not quite exactly right, but sine squared is equal to 1. Right? It's sine squared x plus cosine squared x is 1. So sine squared x is 1 minus cosine squared x. And so that means that this bottom is equal to minus sine of x, right? So this is cosine x plus 1 over minus sine squared of x dx. And now that we have the sum in the numerator of our fraction, we can actually break this up. And we can write this as, we can bring out the minus sign, right? We can write this as minus the integral of cosine x over sine squared x dx minus the integral of 1 over sine squared. I'll leave it like this for now. But that's a trig function that we know the antiderivative of. All right, so this one can be done by u sub. This first one, we let our u equal sine of x, then our du has to be cosine of x dx. And so this first one becomes the integral. I'm going to move the minus inside. Negative 1 over u squared du. That's the derivative of something. And this one is going to be, I'm going to, again, move the minus inside. This becomes plus. And then this one is minus cosecant squared x dx. All right. So this, I hope you remember, is the derivative of 1 over u. So this one's 1 over u. And this is the derivative of cotangent x. So 1 over u plus cotangent x plus c. And then all we have to do is we get our u back in there. Remember, u was sine, right? 1 over sine is cosecant. And so what we end up with, I'll write it down here. The integral of 1 over cosine of x minus 1 dx is equal to 1 over sine. So that's cosecant of x plus cotangent of x plus c. All right, so there's another integral. That one used Pythagorean identity and just a little bit of careful integration techniques. But we got it, right? We got it. So there's 7 examples of integrals involving trig functions. There's a whole lot more in your homework and in the book. So we need to know these because in the future, very near future, like tomorrow, we're going to use trig functions to help us integrate other kinds of functions that are maybe not trig functions to start with, but we're going to use trig to help us. Okay, so I'll see you guys in the next videos tomorrow.